which is relative motion, because we completed projectile motion completely, including doubts and discussions in the last lecture. So let's begin. So in relative motion, what is done is equations of motion are developed to describe the motion of a body particle, whatever be the case, in reference to another moving body or particle. Or you can say that with respect to a reference frame in motion. A very simple example of that is, if you consider a situation like this, that on a road there are two vehicles which are moving opposite to each other. Let's say this one is moving at a speed of 5 meters per second, and this one is moving like this at a speed of 3 meters per second. Now, to a person standing on the ground, what we call the ground frame observer, speed of A appears to be 5 meters per second. Speed of B appears to be 3 meters per second. I'm just writing this as speeds, okay, so not with algebraic sign. But now consider a person standing inside the car or the vehicle B. So to an observer in vehicles A's reference frame. So to him or her, what does the speed of A appear to be? And what does the speed of B appear to be? Can anyone tell me?
Sir, the observer at A may will observe that the vehicle B is at rest and
A is at rest, right? The observer inside A, observe that A is at rest, okay? Because he's inside that vehicle. So to him, it will look like his vehicle is at rest. But what about the speed of B? How much that will appear to be?
8 meters.
Yes, that's correct. It will appear to be 8 meters per second. So this is an example of speed in a relative frame for moving observer. Okay, so just note down this example, then we'll develop the formal equations for this. Okay, so now next thing what we'll do is we'll develop the formal equations of relative motion. So first of all, the general parameters for relative motion equations. So previously the parameters that we have studied in kinematics, they have been position defined by this vector, right? Displacement defined by the vector relation that is change in position delta r. Velocity defined by rate of change of position or displacement with respect to time. And acceleration, rate of change of velocity. So these type of parameters we will redefine here, but we will redefine in context of relative motion. So we'll once again list out and learn how to write these parameters, but in the context of relative motion. So let's understand. The whole idea here. So let's say we have got some general coordinate frame, which is the ground frame. This XYZ system with the origin over here. This is the ground frame. And at some particular instant, there are two particles, A and B, which are generally speaking located somewhere over here. So these are the instantaneous positions of A and B at a given point of time with respect to ground. So here, these are instantaneous positions of what we'll consider in general moving particles A and B at an instant of time t equal to 2. Okay. Now we will see the first definition here, that what we mean by the term relative position. Okay. So therefore, the relative position of, let's say, particle B with respect to particle A, that will be how much? Let's try to understand that. So in our notation, we'll write like this. If we write B comma A, it means of B with respect to A. Okay. So this is of the particle B with respect to or relative to the particle E. So the relative position of B with respect to A is how much? Now we can see in the diagram what we mean by the relative position will be this vector. You shifted your origin to the point A because A has become your reference frame. So with respect to A, where is B located? It is located here. This is the position vector of B in relation to A. So vectorially, you can see it is nothing but the vector RB minus the vector RA. This relative position is the vector, okay, joining B from A to B. So therefore, as a vector formula, it becomes like this. So as a simple example, suppose A is located at the position 1, 2 and B is at the position 3, 5 in a two-dimensional XY plane. These are two particles. A and B are located like this. So the position of B with respect to A, according to this, will become position vector of B minus position vector of A. So it is 3 I cap plus 5 J cap minus I cap plus J cap. So the position of B with respect to A, C will become 2 I cap plus 3 J cap. Because this particular example's diagram looks something like this. So A is located somewhere here, let's say. and B is located at 3, 5. So this vector now joining A with B, this represents the position of B with respect to A. So you can see this vector's x component is 2 and its y component is 3. Hence you can see it as this. Suppose these are in meters. So this position is also in meters. Okay, so we'll come back to the example. Just note down this definition first. Exactly, that's correct. Okay, Ritesh, that's correct. If we were looking at the position of A with respect to B, then it would be opposite to this one because it would be the vector from
Arrow
B
will
to A.
point towards A.
Only the magnitude will change. Magnitude will be the same.
The magnitude will be the same. The direction will be the opposite. Okay.
Yes.
Okay, so one additional important point that we can understand here is that what we are just discussing about, that the position of A with respect to B will be RA minus RB. That is the vector from B to A. So you can see that position of A with respect to B is equal and opposite, equal in magnitude but opposite in direction. Okay. With respect to position of B with respect to A. Okay, so now keeping in mind that A and B are both in motion, therefore, okay, next definition we'll see is relative displacement. This kind of thing. Okay. So now in general, we have seen in kinematics, displacement is defined as change in position. That is final position minus initial position. Therefore, relative displacement will be defined as the change in relative position. So now just looking at the definition of relative position from above, it is position of B in the ground frame minus position of A in the ground frame. So relative displacement becomes change in position of B in the ground frame minus change in position of A in the ground frame. So it basically becomes the displacement of B in the ground frame minus the displacement of A in the ground frame. So just becomes something very simple like this. So for example, in one case, if we have a situation where two particles were situated along the same straight line at here and here at t equal to 0. Now what happens is after some time, A reaches here, making a displacement of 5 meters in 2 seconds. And during that time, let's say B reaches here, making a displacement of 3 meters. So now we want to find out the displacement of B with respect to A and its magnitude. And similarly, displacement of A with respect to B and its magnitude. Okay, so just note down this definition and try this example first. During this specified time interval of 0 to 2 seconds, which I'm showing in the diagram above,
Sir,
yes. Yes, tell
sir,
me,
can
Vita.
you just scroll up towards the note?
Yeah, sure.
Yeah, sir. Thank you, sir. Got it.
Okay. Yes, very correct. So we can write this in one-dimensional frame like this only, that displacement of E with respect to ground will become plus 5, or if we write in vector form, we can write it as 5 I cap, taking this as our x-axis. Okay. Displacement of B, we can write in one-dimensional form like this, or if we write in vector format, we can write it like this. Okay. So displacement of B with respect to A, okay, or in vector format, so this will give us the result that minus 2I. Okay. So either way, you can see that the magnitude of the relative displacement will be 2 meters.
Sir, 4.
Sorry, come again.
No, sir.
Got it, no? Okay. Now, similarly, when you look at displacement of E with respect to B, it's going to be plus 2. So look at this relation and you look at this relation. You
Sir,
understand that
will be different, but magnitude will be same.
exactly. Okay. They are equal and opposite vectors. Now, same way, if we had a situation where now supposing in the same situation, initially A and B are lying here at t equal to 0. But now suppose they're making displacements like this. A is moving the same like in the previous example, but B is moving in the opposite direction. So B is moving along the negative x-axis. Okay, and again B moves by 3 meters. And A moves by 5 meters. So now we have to find the same things. Okay, so this time how much should the magnitude be?
8.
Yes, very good, Jitesh. That's correct. Yes, correct.
Sir, so when they are moving closer, when two bodies are moving closer to each other, like uh, the relative motion will be more.
Yes. Okay, so in this case, you will see that individual displacements of A and B are 5 I cap and minus 3 I cap, or if we write in scalar notation, they are plus 5 and minus 3. So displacement of B with respect to A is minus 8 I cap, or displacement of A with respect to B is 8 I cap. Okay. So the magnitude of each is equal to 8 meters. Okay, now let's see another type of example. So in this next example, let's say we have a situation where two particles A and B are located at the origin O of an xy plane at t equal to 0. Now A moves uniformly along the x-axis at a speed of 10 meters per second. B starts from rest and accelerates along the y-axis with a uniform acceleration of 2 meters per second square. So find the relative displacement of A with respect to B at t equal to 4 seconds. Make a diagram to justify the answer. Yes, very good. Jitesh, Vedant. Jitesh, just check your numerical answer. The concept is correct. Raghu, you'll have to do a vector analysis here, no, beta, because it's a two-dimensional situation. One object is moving along the x-axis, the other is moving along the y-axis. No?
Okay,
So you have to understood, no? It's not along the same axis. This is along the x-axis, right? Whereas this is moving along the y-axis. So we'll
Yes,
just
sir, got my mistake.
so you can do the question just by equations also, but I will first draw a visual picture to understand it better. So what is happening is that A and B are both located at the origin of our coordinate system initially at t equal to 0. They're both located at the origin. But then what happens is that A is moving like this with a constant velocity of 10 meters per second. So its acceleration is 0. Okay. Whereas B is moving with a constant acceleration of 2 meters per second square. Initial velocity of B is 0. So finally, at the given time of 4 seconds, A will be somewhere over here. It will be at 40, 0. That will be its coordinate. And B will be somewhere here. B's displacement will be half 80 square along the y-axis. 16J cap.
Sir, after that 20 wala answer, I gave you another also. Is that correct?
Yeah, that's correct, Nitish. So B's position in the diagram you can see will be at 0, 16 at t equal to 4. A's displacement would be its uniform velocity into time along the x-axis. So at this particular instant now you can see that the relative position of B with respect to A or A with respect to B, whichever we write. If we are writing A with respect to B, it will be this vector. So this is the displacement of A with respect to B.
Sir, magnitude will be 12.
Yeah, magnitude is fine. We can work that out as a vector thing. Okay. So you can see that from 0 to 4 seconds, A's displacement is coming out to be 40 I cap, and B's displacement in the ground frame is coming out to be 16 J cap. Okay. So for this, we are using the idea that A's displacement is like this. And for this, we are using the idea that B's displacement is like this. So relative displacement of A with respect to B So when we are looking for the answer in vector form, this is what we mean. But if you want to calculate the magnitude, Let's do it this way. Yes, very good, Raghu. That's correct now. Okay, so now from this we move on to the concept of relative velocity. So we are looking for the expression of velocity of a body B with respect to another body A. So remember, in kinematics in general, we define velocity as rate of change of position or rate of change of displacement. So here we will define relative velocity as the instantaneous rate of change of relative position or relative displacement. This one should also be B with respect to A. So now using that definition, relative position of B with respect to A is the difference of their positions, or relative displacement is the difference of their displacements. So you can see that this will become ultimately will become rate of change of RB minus rate of change of RA. So that is nothing but the instantaneous velocity of B in the ground frame minus the instantaneous velocity of A in the ground frame. So we're getting a same pattern of all the definitions. Like we saw that relative position is difference in the absolute position of ground frame. Relative displacement is difference in displacements with respect to ground. Like that, relative velocity is vector difference of VB minus VA. And like that, we will see in the next derivation that we do that relative acceleration also comes out to be acceleration of A minus or B minus acceleration of B. So this is a series of definitions that we see. Okay, so now let us understand the application of this with a question. So let's say this is the overhead view of a road, a straight expressway kind of road. In this we have truck which is moving with a uniform velocity of 54 kilometers per hour, and the truck is $10 meters long. Now at that given instant when we are observing this, there is a car which just about starts to overtake the truck. So the car is going at a uniform velocity of 90 kilometers per hour, let's say. And the length of the car is 5 meters. So at t equal to 0, a car just starts to overtake a truck as shown. Assume both move at uniform velocities during the overtake. So first of all, find the relative velocity of the car with respect to the truck. So that is, if a person is sitting inside the truck, in his or her reference frame, what is the velocity of the car they will see. Secondly, find the time taken for the overtake to be completed. And third, find the road length, that is the length of the section of the road needed to overtake. Okay, so just try out this question. Yes, very good, Soham, that's correct. Yes, Vedant correct, Soham correct. Soham, check the answer for the time, okay? Yes, Vedant, your answer is correct for time also.
Sir, velocity of car is 90 or 40?
90, 90, Vedant. Only then it can overtake, like it has to be more. Okay. Just write it more clearly for you. Okay, so the first part is pretty easy. You can just use a one-dimensional notation only. Velocity of the truck is 54 I cap in kilometers per hour. the velocity of the car is 90 I cap in kilometers per hour. So relative velocity is very simple, really.
Sir, is it 10?
Yeah, 10 meters per second or 36 kilometers per hour.
Sir, actually, I took 40 first.
Okay. So it is, as a formula, it will be like this. So as a value, it will come out to be 36 I cap in kilometers per hour. If required, you can convert it to meters per second.
Sir, will the road length be 15 meters?
I'll just explain just a minute. First, tell me how much time.
Yes, sir, that is good.
Okay. So see, there are two ways of, yeah, Arya, your answer is correct for both first and second part. So to understand the time taken to overtake, there are two ways we can do this. One is we can observe this from ground frame point of view. So we are observing from the ground frame. This is what we see at t equal to 0. Okay. And this is moving at 54 kilometers per hour, or that is equal to how much? 54 into 5 by 18. So that is 15 meters per second. And this is moving at 90 meters per second, sorry, kilometers per hour. That is the same thing as 25 meters per second. Now, at whatever time the overtake is complete, the situation should look like this. So in this diagram, you can see that this is the displacement of the car. And comparatively, this is the displacement of the truck. So at time t, the displacement of the car should be greater than the displacement of the truck by how much? By 10 meters plus 5 meters. So this is one way to understand it. Okay, so the displacement of the car will be 25t in meters. But the much easier way of solving this is that it is just solving the problem in ground frame. Now, what if I was actually observing from inside the truck? So, in the truck's frame, what you see at t equal to 0 is you see the car coming at a velocity which is this relative velocity, which is 10 meters per second. By the time the car has completed the overtake, at t equal to t, it's here. So this, from here to here, this is the relative displacement of the car with respect to the truck. And this should be equal to 10 plus 5, 15 meters. So the relative displacement of the car in the truck's frame should be the length of the car plus the length of the truck. So that relative displacement will be relative velocity into time. So this is the much easier way actually to handle this part. The advantage of relative motion, that in that frame, the truck is becoming stationary. You're only having to observe how the car is moving with respect to the truck. So the car is going past the truck such that initially when it started the overtake, the front end of the car was just alongside the rear of the truck. And by the time the overtake is completed, the car is completely gone past. So the rear end of the car should just about come alongside the front end of the truck.
Sir, in the third,
Yes.
to consider the length of the car while it was behind the truck too.
No, it is the time taken for overtake to be completed. No? For road length, it's a different matter. But for second part, no, we are considering the time taken for the overtake to be completed. No? So in that, we have to consider what is the displacement of the car. No? Understood? No? So the displacement of the car, you can also consider like this, from this to this. This is also the displacement of the car. In this case, with respect to the truck. Okay, now in the two diagrams that I've drawn, to understand the road length, that is how much length of road is utilized for making the overtake completed, you'll actually have to refer to the first diagram only. Okay, you cannot judge the road length from the relative frame, because in that relative frame the road is actually moving backwards. No? So you have to judge it from a frame where the road is stationary for you. So that is the ground frame. So now from the above diagram of the ground frame, try to understand what is the road length first of all, and then from that you can understand how to calculate its value. Yes, Vedant, I will just answer your question in a moment and you'll understand. Okay. So if you actually just look at this diagram, you'll understand that what is the total road length that is being utilized. Okay. It is the patch of the road in which, from the beginning of the overtake at t equal to 0 to the completion of the overtake, which we have now calculated to be 1.5 seconds. Okay. It is the amount of road length that is being utilized, or that is, being occupied by this system, which you can think of like the combination of the car plus truck. This system is occupying how much of the road from the beginning to the end? It's occupying up to this point, starting from this point. So this is the total road length being utilized. So this is, let's say, T, which is the road length that is occupied by this system from 0 up till 1.5 seconds. Okay. So you can see that it can be written as the length of the car plus the displacement of the car, or it can be written as twice the length of the car plus the length of the truck plus the displacement of the truck. So length of the car is 5 meters. The displacement of the car is velocity of the car into time. So this is the road length that is required to complete the overtake maneuver. Okay. So hope your query is now clear, Vedant. No? You understood the concept. Very good.
Sir, so we have to add the car length also there, no?
Yes. Basically, you have to understand the diagram, no? That from the beginning of the overtake to the end of the overtake, what is the total length of the road that is occupied by the system? No? So it is from the rear end of the car in the first diagram, right up to the front end of the car in the second diagram. No?
Yes, sir. Actually, mine was coming 37.5. I forgot to add second.
But now you understood now why you have to add the length of the car to that.
Yes, sir, because it covered the, it gone it got ahead of truck, and
Yes.
it covered its own
And
length
another
also.
5 meters. Yes, exactly. Okay. Okay. Now let's look at another example of relative motion, relative velocity rather. Okay. So in this next example, again we have a situation like this. So we have this situation at time t equal to 0. Cars A, B, and C are like this. Now this is moving at a speed of, let us say, 30 meters per second. This is moving at a speed of 20 meters per second, and this is moving at a speed of 20 meters per second. Now at this particular instant, this distance between them is 200 meters, and this distance is, let's say, 300 meters. Okay. So 3 cars are moving at uniform velocities. Ignore the size of the cars and treat them like particles. Just assume they are very small cars. Okay. Compared to these distances of 300 and 200 meters, let's say they are like go-karts or something, so hardly a meter or something long, so you can neglect the size. So find the relative velocity of A with respect to B and C with respect to B and C with respect to A. And then find the time at which A overtakes B and A crosses. He's going in the opposite direction on the opposite lane. So this should also be relatively easy, just to get you used to the sign convention and all when using relative motion in 1D. Complete this quickly, then we'll move on to two-dimensional examples. Yes, Vedant is correct. Yes, correct. Very good. So I'm just putting up the answers first of all for this. Okay. Then if required, we'll discuss any of these. So the velocity of A with respect to B will be plus 10. Okay. And that is why you will see that the time that it takes for A to overtake this time, let's say T1, will be the relative displacement that A has to make divided by the velocity. So it has to cover 200 meters at a relative, so it should be 20 seconds. Okay. Now the velocity of C with respect to B will be minus 40 meters per second. And the velocity of C with respect to A will be minus 50 meters per second. So likewise, the time at which A crosses C, okay, this has to be the displacement that A makes with respect to C divided by the velocity of A with respect to C. So he has to make a displacement of plus 300, but at a rate of plus 50. So it will be at 6 seconds. Oh, sorry, it has to make a displacement of 500. My mistake. So this part is easier to work out if you do it like this, that imagine you are sitting inside the car A. So at t equal to 0, or let's say we are sitting inside the car B. So at t equal to 0, we are seeing A. With a relative velocity of 10 meters per second, but at a distance of 200 meters. Now when the overtaking happens, is here. So this displacement so this is the easy way of understanding the second question's A part. Okay, now similarly, when I look at the B part, if I look at the motion of A relative to C now, and that's also something very interesting. A has a velocity with respect to C of, in this direction, how much? 20 plus 30, right? 50 meters per second. And it's here at t equal to 0. Whereas your observer is now sitting inside C. So initially he's at a distance of 500 meters. Okay. Now by the time he crosses C, it should be this situation. So this time, this displacement of A with respect to C, that should be equal to 50 T2. So from here you can see that T2 should be equal to 10 seconds. You can also try understanding this from the ground frame point of view. In the ground frame, this was the position initially. So at, for example, at t equal to 10 seconds, A would be somewhere here and C would be here. And B would be 200 meters beyond. So B would be somewhere here. So this would be the situation at 10 seconds. So C would have traveled 200 meters. A would have traveled 300 meters. Okay. And B would have traveled 200 meters like this. Okay. And then later at t equal to 20 seconds, rather t1, which we written earlier. By the time it's 20 seconds, B is somewhere here. A is also here. But by then C has reached somewhere here. This is at this time. So this is the kind of situation you will see at that moment. Okay, so people, we're out of time, so we'll pick up two-dimensional examples in the next lecture. But you
Yes.
can look up some of the solved examples from H.C. Verma of relative motion. Towards the end of the solved examples, there are examples where you are, for example, looking at relative motion of falling rain with respect to a moving observer. Okay, how the rain appears to be slanted because of relative motion concept, which is
Yes.
something that commonly you observe also. If you're driving in a car pretty fast, then the rain appears to be quite slanted. If you slow down, then the slant becomes less. So that is again because of the phenomena of relative motion. So we'll discuss about those things in the next lecture. But also don't forget you have your test coming up on Sunday. So do a thorough revision of projectile motion, especially projectile motion on inclined plane, projectile motion with respect to elevated point, and if any last moment doubts and questions come up, please let me know via WhatsApp, or I will try to pick it up either by sending you some hints or maybe some mentorship session during that I can include you and clear the doubt. So that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir.